Hello everyone, welcome back to the another session in design and analysis of algorithms. The topic is NP-hard graph problems. This topic you will find in 5th unit as topic number 5. Now let's get started. NP-hard graph problems. We have a strategy which we adopt to show that a problem L2 is NP-hard, and that strategy is what? We will be having 4 steps, and this is step 1, step 2, step 3, step 4. The step 1 is what? Pick a problem L1 already known to be NP hard. To prove a new problem is NP hard, take one problem which is already NP hard. Now L2 is a new problem, L1 is already you know it. So L1 is already belongs to NP hard. L1 is belongs to NP hard set. Now L2 I wanted to prove that it is NP hard. Then what I am doing is I am taking L1 problem into consideration. Second is show how to obtain an instance of L2 from any instance of L1 such that from the solution of I we can determine the solution to instance of L1. So that is what polynomial deterministic time. The third step, the second step will get repeated till you reduce L1 to L2. Now the fourth step is conclude from step 1 and 3 and the transitivity of reduction that L2 is NP hard. What is transitivity reduction? If L2 is belongs to NP hard, if L1 is belongs to NP hard, depending the property of transitivity reduction is what? L2 is also belongs to NP hard because you found the instance of polynomial deterministic time from L2 to L1 such that now L2 is also belongs to NP hard. So we will be going to prove that in the case of we'll take one thing and we will prove that. So before we'll move to that, an NP hard decision problem L2 can be shown to be NP complete by exhibiting a polynomial time non-deterministic algorithm for L2. All the NP hard decision problems we deal with here are NP complete. The construction of polynomial time non-deterministic algorithms for these problems is left as an exercise. Now we'll do one problem now. So this is what actually proving we were chosen L1 problem which is NP hard. To decide L2 is also belongs to NP hard. So to choose L2 to find L2 is a NP hard problem, you were taken L1, right? So now this is what solution, how to prove it. So that is what we will be taking a polynomial time transform. These are what instances, I and I dash are instances. L2 is actually has to get prove it is NP hard problem. So we choose an L1 which is already NP hard. So it is having some instance which is I. Now NP problem is having instance of I dash. Now polynomial time transform that I dash, if I and I dash are the same instances, then we say that L2 is belongs to L1 because as far as the instances are considered, polynomial deterministic time instances are considered, L2 is L1. So we'll reduce that L1 to L2 depending upon the transitivity closure property. Now we'll solve one problem. The problem is what? Click decision problem. The most important as far as the external examinations are considered, click decision problem. To understand this problem, this problem is what? NP hard graph problem. This problem is NP hard graph problem. So I considered here few graphs. Now these graphs are what? Complete graphs, right? So I say this is complete graph. How can you ensure that it is a complete graph? The complete graph, the one of the property is what? The number of vertices is equal to n. The number of vertices is equal to n. What about the number of edges? The number of edges is equal to n into n minus 1 by 2. Now substitute and you will come to know all these are completed graphs. So what is the n value in the case of this graph? N value is 4. That means 4 into 3 by 2. Answer is here 6. Did you find 6 edges? Count it 1, 2, 3, 4, 5, 6. Now it is a complete graph. And come to this. And I say it is a complete graph. Now to make sure that, find out the number of edges according to this formula. That means number of vertices are 3. 3 into 2 by 2. 2 will get cancelled 3. That is 1, 2, 3 edges. Perfect. Now it is also a completed graph. N into n minus 1 by 2. That is 2 into 1 by 2. You will be having 1. So it is also completed graph. So the graph what I have drawn over here, all completed graphs. Now to understand CDP, that is to understand click decision problem, we add one vertex to all these graphs. Then we'll come to know what is click decision problem. That is, I am adding number 5 vertex to this graph, completed graph. Now 5 is connected to 4 and 3 but not to 1 and 2. So it is not a complete graph. So as far as complete graph is concerned, each and every vertex has established an edge to the other vertex. So according to this definition, you don't have any edge from 1 to 5 and 2 to 5. So 1 to 5 you don't have edge, 2 to 5 you don't have edge, hence it is not a completed graph. Now the same case here. So you added 4, 5 vertices over here and you did not establish any vertex, any edge from one vertex 1 to 4 or 1 to 5. It is also not completed graph. Correct? Now, so what is click decision problem? So basically, click is what? A subgraph. Click is a subgraph of graph which is complete graph. Now, how I can say it is a subgraph? So when you consider it a graph, now in this graph, if you find a complete graph which is subgraph. So this graph is having subgraph, right? Now I am making this is what? Subgraph. The subgraph is what? Complete graph. So click is what? Click should be a subgraph of a graph which is complete graph. So this is what? Complete graph. Now I can say it is having one click. So I can say it is having one click. K is equal to 1. Now here I am denoting K with the number of clicks. And look at this. So is it a complete graph? No. At least the subgraph is a complete graph. Yes. Now this is a subgraph and it is a complete graph. I can say it is a click. And you can take the other example also to find what clicks are available. So now I'm taking the example. This is what previous question paper example. So find out any clicks are available in this graph. Now, so I'm just taking, there is a click of size 4. Complete graph is formed with the 4 vertices. Then the K value is what? 4. K value is 4 in the sense what? Earlier we wrote K is equal to 1. That means what? It sounds that I have only one click. But basically you should not tell that how many clicks you have. You should tell with what vertices you form a click. So K value represents what vertices you have a click. So it is one complete graph and it is a subgraph of one graph G. Now with what number of vertices click has formed? K is equal to 4. So now this is 1. And is this true that I can form with K is equal to 3 also? Yes. And this is one more subgraph. Correct? So it is also a complete graph with 3 vertices. Now is it true that I can form even with K is equal to 2? Yes, it is also a click. So if I take 5, 6, that also a click. So now let us understand what is decision problem and optimization problem. You might have understood this, how many clicks you have. The maximum number of clicks are 4, right? Now let's see what do you mean by decision problem and what do you mean by optimization problem. Decision problem is what? Is there a click of size 3 in the graph? Means the decision is what always? We'll say decision in the sense yes or no or true or false. As far as click decision problem is considered, we will be given with a graph to find out whether clicks are there or not. then what answer we have to say? If clicks are there, we'll be tell it is true or it is yes. If clicks are no, we'll say it is false or it is no. So that is what click decision problem. Click decision problem is what? The problem which require answer is yes or no is a decision problem. Regarding of what yes or no is to find out whether click is there, whether clicks are there. Optimization problem is what? The maximum size, it's a maximum size of click in the graph, the maximum size. So this is what it says, whether clicks are there. If it is there, how many it is there, the maximum size we will be telling. So that is what actually decision problem and optimization problem. So decision problem, we will be considering the value with its k. That means find of a graph is having a click of size k or not. That is what decision problem. And optimization is what? We'll find maximum click in a graph. So basically that CDP, click decision problem, is a graph problem, and also we have to prove that it is a NP hard problem.